They attract. They repel. And they put a new spin on modern technology. From your car to your computer. From high-speed trains to high-tech space propulsion. Harnessing a fundamental force of nature, as perplexing as it is powerful. Now, magnets on Modern Marvels. Welcome to Six Flags Magic Mountain in Southern California. Here, thrill seekers are taking the ride of their lives on the attraction called Superman. A roller coaster that owes its extreme propulsion and popularity to magnets.
Six Flags wanted to build a roller coaster that went where no coaster had gone before, and that was to break the 100-mile-an-hour barrier. In order to get the speed with conventional coaster technology, we would have had to build a lift with a chain probably close to 500 feet tall in order to get that.
Ride engineers had to find a more innovative solution.
So we turned to magnets and electromagnets in order to generate an acceleration of the car that would break every record that was ever known in the roller coaster world.
Superman uses magnetic devices called linear synchronous motors. Although the technology is complex, the underlying principle is elegantly simple.
Everybody remembers from when they were kids where you had a magnet with a north pole and a south pole, and if you took another magnet and got the two north poles together, they'd repel, put the north to the south, and they would attract each other. And that's fundamentally how this technology works on the ride.
You have magnets on the car. You have electromagnets in the track, and the electromagnets can produce repulsive and attractive forces to move the car. And as soon as the car gets to the place where it's being attracted, the electromagnet changes its polarity, the current changes, and attractive force turns to a repulsive force. And you keep doing this in synchronism with the motion of the car and produce constant motion.
Banks of computers and switchers shift the electromagnet's polarity in milliseconds. This enables the cars to accelerate from a dead standstill to over 100 miles per hour in just 7 seconds.
To this day, it remains in the record books as the tallest and fastest roller coaster, and we couldn't have done it without magnets and electromagnets.
We rely on magnets for a lot more than thrills at the theme park. They're everywhere, playing a key role in virtually every kind of technology. From our microwaves, to our computers, to our cell phones.
Throughout our house, throughout our car, throughout any office, there are dozens and dozens of magnets doing their work, but without being seen, out of sight, out of mind.
We use magnets without hardly thinking about it every day. Hidden on the stripe of your credit card are little areas of magnetization, like a barcode. And when you swipe that through the card reader, that barcode information is downloaded to the computer.
For many of us, our reliance on magnets goes hand in hand with our inability to fully fathom how they work.
Magnetism is fascinating because of the mysteries. When you have things pulling at a distance without contact, certainly we understand when I push this hand against this hand where the forces are coming from. But when I take a North Pole and bring a North Pole close to it and they push apart, I don't see any contact. And that is always puzzling to people.
Well, a magnet is simply an object that attracts iron. It attracts some other objects that are similar to iron, like cobalt or steel, but it does not attract other things like wood, glass, plastic, copper. So it's a very selective attraction force.
This selective force also has a handy knack for passing on its properties to the iron objects it touches.
This is a bar of steel. Right now it's not magnetized. To show that this is not magnetic, I'll just simply bring it down to the pile of paper clips and nothing gets picked up. All I'm going to do is touch the north pole of this magnet. Doesn't matter what pole you touch. Now, this bar of metal becomes a magnet.
A magnet works its magic by extending its force invisibly beyond itself, creating what's known as a magnetic field.
Now we can make that visible so you can see it with some iron powder. And I'll cover the magnet up and put a white piece of paper on there so you can actually see it. And I'll sprinkle some iron powder. These are little tiny particles of iron that will trace out the magnetic field. It's collecting a lot of powder right between the poles, but looping out into space are these magnetic lines. Returning to the South Pole, traveling through the magnet again, and exiting the North Pole in a circular looping fashion.
To understand how a magnet is able to generate its field, we must look to the atoms from which they're made.
If you look at the model of an atom, surrounding the nucleus in orbits are these electrons. These electrons are charged particles. That constitutes a magnetic field. So atoms can be atomic magnets. That's the reason something is magnetic, because of those atomic magnets.
The paired electrons of many substances, however, spin in opposite directions, canceling out their respective magnetic fields. Magnetism results only when more of an atom's electrons are spinning in one direction than in the other, free to emit their magnetic fields. The atomic properties of magnets vary. There are so-called permanent magnets and temporary magnets, like the small bars on CD packages, which can lose their magnetism. To prevent one from triggering the security alarm after you buy a CD, the clerk uses an electromagnet to neutralize or degauss its magnetic field. And what exactly is an electromagnet? Like the name implies, it's any magnet that requires electricity in order to function. Kids have been making the simplest versions for decades. Just wrap some copper wire around a nail and attach the two ends of wire to a battery. The electric current flowing through the coil creates a magnetic field, and the nail becomes a magnet. Disconnect the wire and the magnetic field vanishes. Perhaps no one values an electromagnet more than the junk man. At Columbus Auto Shredding in Ohio, magnets surging with electricity make quick work of scrap metal, bound for recycling centers.
This particular machine works with joysticks, right and left hand. And we swing the machine over the material, stop it, maneuver the boom into place, let the magnet down onto the material. We activate with the right hand the magnet. We've got the material attached. We pull the boom back, pick it up. We swing it over the truck. Then we let it down into the bed, and then we use the left button to de-energize the magnet, let go of the scrap.
This 6-foot wide magnet, capable of hoisting more than 5,000 pounds, was crafted here at Ohio Magnetics, just outside Cleveland. Its workers have been churning out king-size magnets for the steel industry since 1917.
This is one of our Ohio Lodestar magnets. This is not a magnet unless electricity is running through it. The electricity comes in through the external magnet leads, goes into the terminal box, and down into the magnet coil.
Manufacturing an electromagnet this beefy requires several exacting steps. It all starts with a roughly cast carbon steel case. This will house the coil that will carry the magnet's electric current. The first step is to flip the case upside down so a boring mill can hone its interior. This will ensure that the coil will fit inside it precisely.
I had to check my measurements after every cut That's to make sure that I'm not going over or I'm not undersized. The most important dimensions to hold inside of this case here is the inside diameter and the center core diameter. So the coil can fit in there properly and rest on the bottom and on these shoulders here.
The precisely machined case is also tailored to fit the bottom plate of the magnet, on which the coil will be wound.
This is the bottom of an electro scrap magnet. The bottom will get a layer of insulation, and then around here we'll wrap the aluminum conductor.
Thin strips of aluminum form the coil, tightly wound around a core fixed to the bottom plate. A thin strip of paper called Nomex is layered between each wind. The Nomex electrically insulates the adjacent layers of aluminum from one another to prevent shorting. After the coil assembly is complete, a welder fuses the case and the coil assembly together. Then, workers pour in a proprietary insulating compound that will fill the cavity remaining in the case. The compound will prevent the coil from contacting the inner wall of the case, again eliminating the possibility of electrical shorting. It will also act as a shock absorber as the magnet impacts against the material it lifts. And it will help the magnet keep its cool.
Heat is a magnet's worst enemy. A magnet will lose about 25% of its lifting capability during a day's operation. The role of the compound is important because it transfers heat from the coil to the outside of the magnet case, and then air, which is around the outside of the magnet, cools the magnet to allow the magnet to efficiently operate.
To cure the compound inside the magnet case, workers transfer the assemblage into an oven where it bakes at 325 degrees Fahrenheit for 12 hours. Then, after the magnet passes a series of tests, it's ready for action. As we've seen, lifting magnets make all the difference at facilities like Columbus Auto Shredding. But they aren't the only kinds of magnets the company relies on to extract the recyclable iron and steel. In its processing plant, where derelict cars have an appointment with doom and the ravenous shredder, a variety of magnets await the mangled remains. It'll be their job to separate the iron and steel from the mass of debris. First, conveyors move the shreds beneath these rotating drums. Inside the drums, magnets set at fixed positions direct their attractive force down toward the passing fragments. The magnets draw them to the drum's surface, where they adhere until they're rotated up and out of the magnetic field's range. The shreds then fall to a conveyor. The uncollected shreds move to another magnet, set within the body of this rotating belt, to separate the iron and steel the large drums may have missed.
The magnet is in the center, and what happens is material is processed underneath the magnet, picked up by the magnetic field, and then moved out by this conveyor belt until it gets beyond the field of the magnet where it is dropped off.
On average, the plant's magnets separate 500 tons of iron and steel each day, which the company then sells to recycling dealers. At the junkyard and across the globe, magnets may not always attract a lot of attention, but their contribution is undeniable. One of the most ubiquitous varieties is hanging around in your kitchen. To make it, you have to shake, rattle, and roll. Many cows have magnets placed in their stomachs to attract nails, wire, and other accidentally ingested metals that could harm their digestive tracts. A magnet can safely remain there for the duration of a cow's life. Magnets will return on Modern Marvels. We now return to magnets on Modern Marvels. In our world of technological wonders, magnets are the forgotten stars, performing their vital functions so invisibly we ignore their presence. And of all our unheralded magnets, the one we take most for granted is the enormous one right beneath our feet. The Earth is a giant magnet. An ocean of molten iron at its core generates its magnetic field. The field streams out at the North Magnetic Pole, loops around the planet, and returns through the South Magnetic Pole. This invisible force shields us against the lethal winds of radiation emitted from the sun and distant stars. You can observe this drama in the skies above the Arctic Circle. The cosmic light show called the Aurora Borealis results when the Earth's magnetic field traps solar particles in the atmosphere and deflects them toward the pole. Closer to home, a more mundane variety of magnet plays a slightly less crucial role in our existence, as it clings to the appliance we visit about 11 times each day. Refrigerator magnets have enabled us to turn this nucleus of the American home into an information center and art gallery. Ever wondered where these indispensable little gadgets come from? There's no better place to start looking than FlexMag Industries in Marietta, Ohio.
There's at least a 50-50 chance that the products on your refrigerator were made at this facility.
FlexMag rolls out up to 100,000 pounds of magnets every day. From the strips that secure your shower door to the signs you can stick to the side of your car.
The two main materials that we use in our flexible magnets are synthetic rubber and then also ferrite powder. This material is made from strontium carbonate and iron oxide. This magnetic powder is only very finely magnetic. As you can see, it doesn't really stick to itself very well, so it has to be very fine and airborne before it'll stick to anything metal.
This is where the life of your fridge magnet begins, in what FlexMag calls an intensive mixer. After workers throw in the rubber, bags and all, the ferrite powder showers on top of it.
We use rotors to distribute the material evenly, and then there's a large ram that puts pressure on the mix as it is mixing. Between those two, we get an even distribution, and we readily mix the ferrite throughout the rubber. It takes approximately 5 to 7 minutes to run a batch. Once the material is discharged from the intensive mixer, it's not in a format that we can use, so we dump it into what we call a batch extruder. We maintain the temperature of about 275 degrees through this process in order to keep the material so that it's able to extrude it easily.
Next, conveyors transfer the extruded compound to other machines that granulate and cool it. Then the powdery mixture passes through heated rollers that press it into a thin sheet. At this point, this humble material wouldn't stick to your fridge or anything else metallic. But now it's finally ready to pass over the simple device that'll turn it into a magnet. It's a roller consisting of powerful permanent magnets classified as rare earths. These particular rare earth magnets are neodymium iron boron and are positioned such that their north and south poles alternate along the length of the roller.
Before the sheet passes over this roller, the small ferrite particles in there are really not aligned magnetically in any form or fashion. As they pass over this, the field that is produced off of this rare earth magnetic roller aligns those little particles in the sheet to create a magnetic pattern on the sheet. And those would be a mirror image of what this magnetic pattern is on this roller.
Seconds after the sheet's bottom side is magnetized, a machine laminates its non-metallic top side. This is the side that'll stare back at you from your refrigerator, emblazoned with everything from calendars to the phone number of your local pizzeria. But before FlexMag ships the rolls to its clients who apply those touches, how can it be sure of its product's stick-to-itiveness?
One of the ways we make sure that the magnetic material is actually magnetized is we use sheet vellum. The vellum is actually two thin pieces of plastic with a liquid medium in between that holds fine magnetic particles that align with the magnetic pattern. And this material will show you the magnetic imprint on the magnetic sheet. As you can see, it's the same magnetic imprint that we used on the rare earth magnet roller.
Magnets have been leaving their distinctive mark on civilization for more than 2,000 years. And it all started with the discovery of a curiously attractive rock. Earth's magnetic poles have changed places hundreds of times over the past 400 million years, reversing the direction of its magnetic field. The last reversal occurred about 780,000 years ago. Magnets will return on Modern Marvels. We now return to magnets on Modern Marvels. For centuries, scientists have attempted to solve one of the animal kingdom's most perplexing mysteries. How do some species regularly navigate vast distances across the globe without getting lost? Recent studies suggest an intriguing solution to the puzzle. Researchers believe some animals use tiny natural magnets in their bodies that enable them to sense the Earth's magnetic field.
There is some evidence that birds and animals and fish use the magnetic field lines of the Earth to help them in their migration. They can find their direction, much like we do with a compass.
Just as animals may use magnets to survive in nature, we use them to sustain ourselves in a world of mechanization. Our enduring relationship with magnetism dates back to antiquity. About 2,000 years ago, the ancient Greeks and the ancient Chinese independently discovered Earth's only magnet crafted by nature. It became known as the lodestone, or magnetite.
It's an oxide of iron, and the basic properties of the lodestone come from its atomic structure, but how it's magnetized is still a bit of a mystery. We think there was lightning strikes hitting the rock and the magnetic fields from the lightning magnetizing the rocks.
Chinese innovators used the unusual mineral as part of a device made of polished brass. On its surface, a spoon-shaped lodestone was free to rotate in response to the Earth's magnetic field. It marked man's earliest step toward the first practical application of magnets: the compass. A compass's magnetic needle determines direction by aligning itself with the Earth's magnetic north and south poles.
If I place this in a little cup and allow it to float on some water so it's free to rotate, the compass will turn around and align itself pointing at the South Pole. If I reverse the magnet, the compass senses that the pole has changed and points the other way. Reverse it again, it swings back around.
By the 13th century AD, the compass changed the face of sea travel, relieving sailors from plotting their courses solely by the sun and stars. When storms obscured the skies, they could still ably navigate. In the centuries to come, the curious began to slowly unravel magnetism's mysteries. William Gilbert, physician to England's Queen Elizabeth I, led the way in 1600 with his landmark treatise, De Magnete. It was Gilbert who first concluded that the Earth was indeed a giant magnet. More than 2 centuries passed before an accidental discovery produced the next crucial breakthrough. In 1820, Danish physicist Hans Christian Ørsted stumbled upon magnetism's inextricable relationship to electricity.
Hans Christian Ørsted was the first to demonstrate that electric current down a wire would produce a magnetic field. He just had a compass needle near a wire. When the current went on, the compass needle turned. When the current went off, the compass needle turned back.
And he thought this was very curious. This discovery tied together 2 separate disciplines, electricity and magnetism. Ørsted discovered that they're really one and the same thing.
A decade after Ørsted discovered that electricity creates magnetism, English scientist Michael Faraday demonstrated the reverse, that magnetism can produce electricity. He found that moving a magnet near a stationary coil of wire, or moving a coil of wire within a magnetic field, induced electric current.
The oscilloscope is connected to the coil, and it reads the voltage that is induced in the coil. So you can see as I move the coil through the magnet, the spot moves up and down in response. The faster you go, the greater the voltage. So if you need more electricity, you have to move it faster.
Faraday's discovery was monumental. It paved the way for the invention of the electric generator, which enabled man to create electricity on a scale never before imaginable. The key to generating the power was to harness some form of mechanical energy in order to put the magnets or electric coils into motion.
In a hydroelectric plant, it's water falling over the dam through the sluiceway and turning the water wheel. In a coal-burning power plant, the coal makes steam and the steam turbine turns the generator. A wind power generator, the wind turns the blades of the generator. So the process is the same. Mechanical energy converted to electricity.
In the early 20th century, magnets were also empowering the reverse of this process, driving electrical motors that converted electricity to mechanical energy. The motors had eclipsed steam engines as the era's prime movers, propelling everything from trolleys to cranes to elevators. In a common electric motor, an electromagnet called the armature revolves between the north and south poles of a stationary magnet called the stator. The armature rotates until its north pole is opposite the south pole of the stator. The direction of the armature's current is then reversed by a device called a commutator, changing its north pole to a south pole. The two south poles repel each other, pushing the armature forward. The current reverses every half turn, keeping the armature in motion by frustrating its effort to bring north poles near south poles. Magnet-driven motors and generators accelerated the 20th century's modernization through electricity. Two inextricably linked industries powered one another's advancement.
The rise of the electrical industry involved a great growth in the use of magnets. And also these things work together. As the industry grew, magnets got better. As magnets got better, the industry grew. So it was very much a symbiotic relationship between magnets and electricity.
Experts advanced both industries by developing new generations of magnets with ever-improving properties. The first commercial magnets were made from carbon steel and later tungsten steel. These were stronger than the naturally occurring lodestone, but heat and jarring could significantly reduce their magnetism. In the 1930s, researchers created a stronger, more heat-resistant variety called Alnico, an iron-based alloy containing aluminum, nickel, and cobalt. Still widely produced today, they stored greater magnetism in a smaller package. But without an electric jolt, their magnetic potential remained dormant.
You need a very large magnetic field to magnetize them adequately. So what you want to do is have an electromagnet with a large current.
Magnetizing the material is a swift and simple process. Just place the wannabe magnets close to an electromagnet, then turn on the juice. The intense magnetic field realigns the alloy's atoms to make it magnetic. In the 1950s, Alnico magnets were joined by low-cost compact alternatives called ferrites. Today, these iron oxide compounds account for about 90% of the permanent magnet market.
The ferrite magnets allowed motors to be made in a smaller diameter, shorter length, and really the application fitted itself very well for the automobile industry. Now you could have seat positioner motors, for example, that fit very nicely beneath the passenger seat, and window lift motors that were now small enough to fit very nicely into the door of an automobile.
Today, magnets play a key role in not only our cars, but also our computers. Researchers exploring new frontiers in that field are beginning to see the light. The most powerful known magnetic object in the universe is a neutron star, SGR 180620, in the constellation of Sagittarius. Its magnetic field is 1,000 trillion times stronger than Earth's. Magnets will return on Modern Marvels. We now return to magnets on Modern Marvels. No device illustrates the march of miniaturization and advances in magnets better than the cell phone. When retailers unveiled the first generation of models in the 1980s, they were as big as bricks and just about as heavy. Over the years, smaller and smaller transistors helped designers create phones with footprints no bigger than a business card. But without a tiny rare earth magnet for its speaker, a model this petite would never have been possible. Rare earth magnets were first developed in the 1970s and 80s, derived from a group of scarce metals that until that time were very difficult to refine.
They've found that adding these metals to samarium and cobalt together make a very powerful permanent magnet. These are extremely strong. If you take a magnet made of samarium cobalt, just 3/8 of an inch square, and bring them together, you physically have to work very hard to pull them apart.
The mighty and minuscule rare earth magnets have helped power the age of mobile computing. They're an integral part of every laptop's miniature disk drive. The relationship between magnets and computers dates back to the 1950s, when scientists explored the idea of using magnets as repositories for information.
A North Pole up gives one measure of something. A North Pole down gives another measure of things. And once we can say, this is yes and this is no, then we can build a memory device out of it.
Most computers today come equipped with hard drives featuring a layer embedded with tiny magnets. The north-south configurations of those magnets contain encoded information.
The hard drive is magnetic. There's a read-write head in the computer that rides just above this rotating disk, and as it rotates, it writes and reads little bits and bytes of information on that disk. It could be a south pole, and next to it, it might write a north pole, so you'd have a 1 and a 0.
Ones and zeros are the components of the so-called binary language of computers. What would appear to us as an ocean of indecipherable numbers contains data easily digestible by the computer's processor. Magnetic hard drives, however, retain only part of a computer's data. Semiconductors provide its primary memory, in which most of the computing takes place. The semiconductor memory, known as RAM, is faster, but carries a distinct disadvantage. When you shut off the power, the data disappear. Rebooting your computer takes several minutes because it's reloading the lost data onto the memory chips. Researchers, including MIT professor Carolyn Ross, are searching for an alternative, using magnets.
The next big thing that's coming along is called MRAM, that's Magnetic Random Access Memory. And what that is a magnetic chip that you can put in your except that when you turn the computer off, the information stays there. And so when you turn the computer back on, all the information is still there and the computer comes on immediately without having to wait for it to boot up.
To determine which magnetic material might make the best MRAM chip, researchers place samples in a machine called an alternating gradient magnetometer.
This machine has a couple of big magnets. These are electromagnets. So we pass a big current through some coils, and that produces a magnetic field. And it characterizes the magnetic properties of a material, so we can assess whether that will be a good material to use in an MRAM or a hard disk, or other applications like transformer cores, which all use magnetic materials.
As the quest for MRAM continues, researchers at Ohio State University are exploring an intriguing alternative. They've created an unusual magnet that also promises to start your computer in a flash. It's made not of iron or steel, but plastic.
Presently, plastic magnets remain sensitive to the air. So in our research and our development, we keep our plastic magnets in environments which have no oxygen and no moisture.
Researchers produce the plastic magnets by mixing two chemicals, vanadium hexacarbonyl and tetracyanoethylene.
What I have here is the vanadium TCNE that's been deposited on a piece of Teflon tape. The easiest way to tell if it's magnetic or not is to stick it next to a magnet and see if it attracts.
Ohio State's research teams have learned they can manipulate the strength of this magnetism using surprising new methods.
With plastic magnets, you're able to control magnetism in ways we can't control it with conventional metal or ceramic magnets. The plastic magnet has a structure we can address with light.
Experimenting with lasers, the researchers have found they can alter the strength of plastic magnets using different colors of light. Blue light increases the magnet's strength by about 150%. Green light has the opposite effect. It reduces the magnetism by about 60%. Such results hold the promise of recording and reading digital information in a revolutionary new way.
Plastics that are magnetic opens up the opportunity for new kinds of technologies that will have computers that turn on instantly, low power electronics, lightweight ways of storing information.
Experts are confident that magnets will rise to the occasion in all fields of scientific endeavor. Some of magnetism's most intriguing applications are totally up in the air. In 1956, IBM introduced RAMAC, the first computer system to use magnetic disks to store data. It required 50 24-inch disks to store 5 megabytes, about the same amount of memory needed for a typical MP3 song. Magnets will return on Modern Marvels. We now return to magnets on Modern Marvels. There's a magnet in Florida attracting the global scientific community. Housed at Tallahassee's National High Magnetic Field Laboratory, it's the largest and most powerful magnet in the world. It generates a magnetic field about 1 million times greater than the Earth's, making it an invaluable research tool.
Well, the mission of the laboratory, the primary mission, is to conduct science in very high magnetic fields.
The main reason that we seek out these very, very high fields are much the same reason we might measure things at very high temperatures or very low temperatures, very extreme conditions. When you move to new areas, just like Captain Kirk and Captain Picard, when you go where no one has gone before, you are bound to learn some new things.
The jumbo magnet's awesome force results from the combined power of a giant electromagnet and a nitrogen and helium-cooled superconducting magnet. It's so strong, it can actually levitate materials that you wouldn't expect to react to any magnet. This is possible because most common materials, including water and living tissue, are weakly magnetic. They're said to be diamagnetic, meaning they exhibit a subtle tendency to be repulsed by a magnetic field. One intriguing way to demonstrate this diamagnetic force, as well as the unparalleled power of the lab's magnet, is to enlist the aid of an ordinary frog.
Frogs are 90% water, and water's diamagnetic. And let's imagine what happens when we bring a frog near the center of a high magnetic field region. When we do this, the diamagnetic force on the frog gets larger and larger.
It may look like the frog is floating in water, but it's actually suspended in the air. The magnetic field being generated is so intense that it's canceling out the force of gravity. A magnet's power of levitation over everything from frogs to frying pans represents much more than an amusing parlor trick. It offers a world of tantalizing commercial possibilities.
Say you have machinery that you want to spin very, very fast, and ordinary ball bearings won't do because there's too much friction. You could levitate. They're called magnetic bearings. You can levitate the shaft and allow the shaft to rotate it in a magnetic field.
A racier form of magnetic levitation is scorching its way along a 12-mile test track in Emsland, Germany. Here and in Japan, maglev engineers are developing frictionless rail systems that propel trains at speeds up to 275 miles per hour. Wondering how you levitate one of these 60-ton rail cars? The bottom section of the train wraps around a T-shaped track called the guideway. A set of electromagnets lines both sides of the train's undercarriage. An electromagnetic field generated in the guideway attracts the magnets, lifting the train less than half an inch above the track. A second set of magnets lining the train's sides exerts a lateral force, keeping the vehicle properly aligned. If you're looking for the motor that propels the maglev forward, don't bother looking anywhere on the train. It's laid out flat along the guideway. A system of magnets, like that used on Magic Mountain's Superman roller coaster.
This is, for example, another application of the linear synchronous motor. If you synchronize the changing of the poles with the motion of the train, you can keep the forces going.
Train engineers aren't the only ones getting a lift out of magnetic levitation. Scientists at NASA are exploring how magnets can give the spacecraft of tomorrow a boost into orbit.
One of the things that we're investigating that deals with the use of electromagnetic energy is a launch assist system. And this is a ground-based electromagnetic rail with levitation coils and a linear motor that provides thrust to give a launch vehicle the initial velocity from dead stop up to 400 to 600 miles an hour. We have no contact with the ground due to the levitation, and then the linear motor provides the acceleration and the propulsion in the forward direction.
A magnetic levitation launch system would conserve a huge amount of fuel. Fuel that would otherwise be needed to escape Earth's gravity could then be available to propel a craft deeper into space. But some believe magnet technology will play a far more significant role in our quest to reach the stars. Within the next few decades, space propulsion systems could be fueled by superheated gases called plasmas, and magnets may be the key to containing their immense energy.
The particles inside the plasma are charged particles that have very high kinetic energy. That means they're moving. Moving charged particles create a magnetic field. So that means a plasma is magnetic and will respond to a magnetic field.
Experts theorize that magnets would be the only force capable of preventing the superheated plasmas from burning through the walls of the propulsion system. And only magnets could safely direct the plasmas to reaction chambers. If such a system could be engineered, it would power a bold new age of exploration.
This concept would eventually lead to enabling humans to go anywhere in the solar system, anytime they want to go, and at reasonable cost.
From the cosmos to your computer. From roller coasters to your refrigerator, magnets exert their invisible yet indelible influence. They surround us and empower us as a crucial driving force in our lives.